And now, since this is the last class before your class test, at least short class test on Monday, if you have any specific questions about the topics that will be covered there, go ahead and ask. No questions at all? Great.
Sir, I have a question regarding diodes.
Diodes, well, yes. If somebody has a question about the topics that will be covered in the classes, let's take that first. After that, I will take your diodes question. Okay?
Okay.
So, is there anybody who has a question about topics that will be covered in the class test? That is Thevenin's theorem, Norton's theorem, and AC circuits.
Sir, I have a doubt
Yeah.
related to Norton's theorem. In Norton's theorem,
Yes.
sir, we find admittance. Sir, can we do it like finding the resistance and then making it inverse? It will
Yeah,
be
of course, you
easier.
can do that. You can do that. It's essentially that.
Okay, sir.
The reason why we talk about admittance rather than resistance is simply basically when you have a current source, the current is the source is trying to drive current, right? And there the admittance essentially tells you how much current will go. Right? If you have a given voltage source,
Right,
then the
sir.
resistance limits how much current can go in. If you have a current source, then the admittance allows current to go in. Basically, in other words, or more simply put, it's basically like this. Every source has a source resistance, right? Which, in the context of Thevenin's theorem, becomes the Thevenin voltage and the Thevenin resistance. So, when you have an external load, you talk in terms of a load resistance simply because that allows you to calculate things much more directly. You just add up the two resistances and you get the total resistance, you divide that voltage by that, you get the current. On the other hand, when you have a current source, then you think of that as a current source in parallel with an admittance of its own, which is the source admittance. Again, in the context of Norton's theorem, this is the Norton current. This is the Norton admittance. The reason why you think about it like this is pretty simple. You actually also think about a load not really as a resistance, but as an admittance. Why? Because here, YS and YL are in parallel, and for parallel admittances, the admittances add. Okay? Parallel resistances add when they're in series, admittances add when they're in parallel. So the voltage across the output here will essentially be current divided by YS plus YL. So you can see the parallel between these two equations, right? It's as if voltage and currents have been interchanged
Right.
and resistance have been interchanged with admittances. This is the reason why when you talk of current sources, you talk of admittances more than resistances. Look, the same kind of language can be used for both. If the source resistance is small, a voltage source is a good voltage source. Similarly, if the source admittance is small, a current source is a good admittance, good current source, because then almost all the current will flow through the load and not through the source itself. So nothing will be diverted to the source. Whereas here, a small resistance is great because then no matter how much current you draw, the drop across the internal drop across the source resistance will be small. So in both cases, source resistance for the voltage source and source admittance for the current source, they play similar roles. That is why for Norton's theorem, we talk of current sources and admittances rather than resistances. But of course, you can calculate resistance and take the reciprocal. Works the same way. It's just, well, admittances are things which are slightly unfamiliar to you, so you may feel more comfortable working with resistances. However, it's actually easier to work with admittances, especially when you're talking about current sources. So once you get used to that, you will find admittances just as easy to work with. Just you remember that resistances add when they're in series and combined by the complicated RS into RL by RS plus RL rule. If they were in parallel, admittances on the other hand are simpler when they're in parallel. The formula for the series admittance is actually slightly more complicated. It's essentially the same kind of formula as for parallel resistances. Okay, anything else?
Thank you, sir. Sir, I had one more doubt. When we were deriving the Thevenin's and Norton's theorem using the Taylor series expansion, there you mentioned that for small voltages we can take the assumption we took for Thevenin's theorem, and for small current we can take the approximation we took in Norton's theorem. So, sir, what if we took the higher order terms
Sorry,
for nonlinear
if I
circuits?
said that, then I made a mistake. Yes, say that, because basically when you talked about Thevenin's theorem, we were essentially talking of voltage across these two terminals, the V. These two terminals make up a port. Okay, the voltage difference between them was a function of the current. You can think of it like this way, or you can think of the current flowing out and a function of the voltage. Works both ways, right? So if you think of voltage as a function of the current, then you can write this as V for 0 plus dVdi. So dVdi at I equal to 0 into I plus higher order terms. So for small currents, not for small voltages actually, for small currents, you can get to drop the higher order terms. Okay. So in Thevenin's theorem, it's really an approximation which is valid for small currents, not for small voltages. Okay. If I said small
Right,
voltage
sir.
anywhere, I made a mistake.
Sir,
Okay.
I must have made mistake hearing that, sir. I was asking about what if we took higher order terms also, like d square v by di
You
square.
could of course take higher. In fact, okay, there are 2 points here. One is if your circuit is linear, as I've mentioned several times, then this equation is really not an approximation. Then this equation is exact. Okay. So all the examples that we have given so far with resistances, capacitances, inductances, and so on, and ideal sources, they are actually linear circuits. There the voltage is ultimately related to the current in a linear fashion. Okay. And in all of those, this formula is actually exact. There are no higher order terms. However, we will often use Thevenin's theorem for situations like nonlinear circuits like diodes or transistors and other components. And there you do have higher order terms. Okay. So if you want a more accurate result, you would want to take into account the higher order terms, which are typically done using, say, numerical calculations based computer-based programs. Okay. The reason why you want to stop here, even for nonlinear circuits, with the full knowledge that then your calculation will be approximate, is simply because of this, that this expression, if you stop here, can be written as a voltage minus a resistance times a current, R Thevenin, and this is of course what is called V Thevenin. Now, what's the good of that? The good point about this, the great thing about this is that you can actually then replace this by a circuit. Look, V can be a pretty complicated function of I. Okay. How complicated? That depends essentially on what is inside the black box. If there are very complicated nonlinear things inside the black box, V will be a complicated nonlinear function. But even a complicated nonlinear function essentially behaves like a straight line function if you look at a small enough region. In fact, know that I've started with I equal to 0 and then taken a term like this, but we could also have done, especially for nonlinear devices, we often do this. We only consider fluctuations from some basic quiescent point voltage, just like we did for the H parameters or the Z parameters. So we would be sitting on some region, we will talk about fluctuations about that region, then we will essentially have this term. The variation will be this, plus whatever is the bias value. Now, there will be higher order terms, true. But the important thing is, if you stop just here, you can replace this by a simple circuit equivalent, which you could not do if you had higher order terms. Okay. The simple representation with a voltage source in series with a resistance, that essentially is a linear relationship. So what you're really doing is approximating a voltage versus current relationship, which could be a nonlinear relationship, by a linear one. That's what you're really doing at a mathematical level. The reason why you're doing it is twofold. First of all, your circuit may really be linear, in which case there are no other terms. Secondly, even if it is nonlinear, often it is nonlinear, well, nonlinear in a small way, in the sense that it's nearly linear. Then this essentially is a pretty good approximation. Okay. And why do you prefer this approximation over the exact result? Because this allows you to give yourself a circuit equivalent. What's the good of having a circuit equivalent? It's simply that now that you can replace a complicated thing inside the black box with a simple circuit, you can use all the things that you've learned about circuit analysis, all results about, well, series resistances, parallel resistances, all results about the power transfer theorem, all of those can be used pretty straightforward, in a pretty straightforward manner. Okay. So on the other hand, if you had to higher order terms here, say alpha I square plus beta I cube and so on, which of course you would have in a nonlinear scenario. Only thing is we are hoping that these terms are very small. But if they were not very small, then what would happen is that you would have to put in an additional piece which is proportional to the square of the current, and that doesn't have any simple model, simple circuit model. Doesn't mean that such things are not there. Such things are really there. And the good thing about Thevenin's theorem is it gives you, even in situations where the nonlinear terms are significant, it gives you a good starting off point, a good place where you could start your approximations with. And then you can use, if you want more accurate results, you can always use numerical methods to find out more accurate results. For example, the programming problems I gave you could be avoided. In fact, are often avoided in textbooks simply by using some simplified model of the diode. Then you don't have a programming problem to solve, then you can solve it using elementary methods. On the other hand, if you want to talk in terms of the real nonlinear diode behavior, the exponential behavior and so on, or the exponential behavior is also an approximation for diode behavior. But that's a better approximation than the ideal diode behavior. That's all I'm really going to say. So if you want a more accurate result based on a more realistic approximation to the actual diode formula, you would have to do a program, write a program. Or you would have to rely on a program somebody else has written for you. Now, there are plenty of programs available which actually simulate circuit components and do numerical calculations and give you the result. All I was trying to do in the programming problems is to encourage you to write your own programs for specific cases, which you can do very easily. Okay. But nonlinear devices, if you really wanted to talk of situations where nonlinear terms were big, you can't stop here. You have to take the other terms. And then this fails, then you have to actually rely on more complicated nonlinear calculations, either analytic ones, which are very rare, or numerical ones on a computer. Does that answer the question?
Yes, sir. Thank you, sir.
Okay. Anybody else? No questions about the AC part? No questions even about why we use Laplace transforms or things of that kind? By the way, Laplace transforms are very much part of the AC part of the course. So that's also in a possible thing in the exam. Okay, if there are none, let's hear the diode. Okay. Sorry, I've forgotten who asked the diode question. At least you wanted to ask the diode question. Yeah.
Yeah.
Go
So,
ahead.
sir, in the previous video, like we uploaded, you have demonstrated the topic on like modeling the diode. So
Yeah.
I didn't understand like the equivalent diode circuit part. So I didn't understand why do you use the battery in a negative direction?
Okay. That's a good point. So basically what we were doing is something like this. We have this current to the diode plotted against the voltage across the diode. Remember here, in the characteristic curve, what you are plotting is a current which flows through the diode, and VD here is the voltage which is across the diode, not the source voltage. The source voltage will be used when you talk about, say, the set dynamic characteristics. Anyway, this is what ID versus VD graph for a diode essentially looks like. Okay, some kind of an exponentially growing behavior, although even the exponential formula, which can be derived using elementary statistical mechanics, is not precise because it relies on a very oversimplified model of what the diode really is like, but it's pretty close to being precise. So when you want to analyze a circuit with a diode, let's say a circuit as simple as this one. So you have a voltage source, you have a diode, you have a resistance. So what do you have? You have Vs equals voltage across the diode plus IDRL, right? Because whatever current flows through the diode also flows through the resistance. So let's call it IDR. So this is one equation. Okay, how many unknowns do we have here in this problem? If I were to ask you to find out the current, what are the unknowns here? Two, right? One is VD, the voltage across the diode, the other is ID. I may want only the current, but the VD is also unknown. So this equation, which is nothing but KVL, Kirchhoff's voltage law, actually is one equation for two unknowns. We need one more equation. And the other equation is also pretty straightforward. It's nothing but VD as a function or ID as a function of VD, whichever way you look at it. The other equation is simply the characteristic equation. ID is some function of VD. So the point is, here you have two equations, one which comes from Kirchhoff's voltage law, the other which comes from the diode itself. This is the diode characteristics. So you need to solve two equations simultaneously in order to find out the voltage and the current. So how do you solve two equations simultaneously? One way is to solve them graphically. This one is already given in the graphical form. This is really ID was as a function of VD, this curve. And Vs equal to VD plus IDR is another relationship between VD and ID. This relationship is a straight line relationship. Okay. This is nothing but a straight line which stretches from the point Vs0, that is when ID is 0, VD is equal to Vs, to this point, which is when Vs is 0, sorry, when VD is 0, Vs the current is Vs by R. So 0, Vs by R. So this line is called the load line. And the intersection point of the load line with your curve, this is what gives you the actual value of the voltage across the diode and the current to the diode. Now we have also talked about what happens when you change the Vs. Of course, when you change the Vs, this load line shifts parallel to itself. It comes here, let's say. and then you get a different value and so on. But this is one way of handling the problem. You have two equations, one of which was represented by a graph, the other by an equation. What you did was you replaced both by graph. That is, you change the KVL equation, which is a pretty straightforward equation, into a simple graph and found out the intersection. The other possibility could be to actually solve these two equations simultaneously by essentially using this equation directly in a numerical form. Okay, some kind of numerical solution for this complicated simultaneous pair of equations. When I say complicated, I mean the whole pair together is complicated. One of the equations is very simple. It's just a straight line equation, just Kirchhoff's voltage law. The other equation, which describes how the current through a diode changes across with its voltage, is actually a complicated nonlinear equation. That is more complicated than simply the current through a resistance. Now, so of course you can numerically solve this problem. The other thing that you can do, and which is what is being referred to here, is essentially replace this characteristic curve by a simpler model version, which is at least easier than it. So what you do? First of all, you can feed this curve. If this is roughly where your current is, near the region, this curve is almost a straight line. So what you do, and now my drawing skills are going to be seriously tested. But what you can do is replace it by a straight line, something like a tangent to it. Okay, not very clear the drawing, but I think you can sort of understand that what I mean here is this tangent. So what we'll have is an equation, is a situation like this. Instead of the actual curve, I will depict it by a straight line which is flat at 0, and then this another straight line. Straight lines are easier to model. Okay. Now, how do you model this? You model this essentially by, now, what we said was you could approximate this further. You could approximate this, for example, by ignoring this slope, which is actually very, very steep. Even rather than saying ignoring, I should say replacing this already steep slope by nearly infinity, making this a vertical line. And this part, which is actually not 0, so there's a small voltage here, small current here. I'm going to replace that by 0 current. So this is the blue line is the actual characteristic curve. This red line, pair of straight lines, is the next approximation. This is the next approximation where we ignore this, the fact that it is slanted, and the final approximation that we talk about is this one, where we just ignore this small voltage which you have here, the so-called cut-in voltage, and we just put in like this. But this is the ideal diode. An ideal diode is one in which, when there is a reverse bias, no current flows. So when the voltage is negative, absolutely 0 current. And when current is flowing, the diode behaves like a short, so no voltage. So 0 voltage drop across the diode simply because it behaves like a short. But if you try to drive current against it, there will be no current. So you get this nice sharp L-like structure in the characteristic curve, where the knee of the L is exactly at 0. So this is what you model by an ideal diode. Unfortunately, the ideal diode has no special symbol. It uses the same symbol as a real diode. So you have to understand typically from the context whether we mean an ideal diode or whether we mean a real diode. Now what you do is, first of all, mathematically you have this curved line to begin with, which you could have replaced by a complicated equation. I hope I'm still there. Can you hear me?
Yes, sir, we can hear you.
Okay. Sometimes my screen is jumping around. I feel like I got disconnected. Okay.
Yes, sir, your
So
screen
you
is
start,
lagging, but we can hear you.
you can also see the screen, right?
Yes, sir, there is minute lag, but we can see.
Okay, that's fine. So the blue line is the accurate or at least experimentally determined characteristic curve, which can be replaced by some complicated equation. The red line is a very good approximation to this. One slanted straight line, another flat straight line. The next level of, so this is the first level of approximation. This is approximation 2, where you have ignored the fact that this is slanted. And this is approximation 3, where you actually ignore the fact that this is actually shifted. So you are ignoring the cut-in voltage. You are saying that the diode actually starts conducting the moment the voltage tries to become positive. So the ideal diode is in circuit just represented by this. And now comes the next bit, which is what we can do is, depending on the level of approximation you want, you can either replace your real diode by an ideal diode and do your calculations pretending that it's really an ideal diode. That gives you a reasonably good answer, but not a perfect one. You want a better answer, what you should do is you should go in for approximation 2, which is this. Now, this is what the question was really all about. Remember, these two ends are your real diode. Okay. And this is an ideal diode which I put in. And what I'm claiming is that you are putting in an additional battery of size V gamma in the negative direction, opposite to the way the diode would want to conduct. Now, why do you want to do that? Now, notice that when you say VD and ID, VD is the voltage between these 2 points, the 2 ends of the real diode. Okay. So when VD is 0, for example, there is 0 voltage between these 2 ends. Is this ideal diode here forward biased or reverse biased? Yes. When I say 0 volts, just imagine that these 2 points are joined together by a wire. Then is the diode forward biased or reverse biased? Reverse biased, right?
Reverse.
It will not carry any current. Okay. There will be no current. Not through the diode, not outside wire. Now, if VD is say 0.1 volts and V gamma, say V gamma is 0.7 volts, which is a typical value for many diodes, or at least around that. And let's say VD is 0.1 volts. That is, the diode, when you say VD, you are trying to actually make this side positive. So let's say I've given 0.1 volts here. So there's you can think that you have connected a battery here to this side, and you've got 0.1 volts there. Maybe let me just draw it again a bit. This is V gamma and this is your VD. I'm representing it by a voltage, but it could be some complicated circuit which ultimately gives a voltage here. But let's say VD is around 0.1 volts. Is the diode forward biased or reverse biased?
Reverse.
It's still reverse bias, right? Because V gamma is larger than VD, so V gamma overpowers VD. So when will it become forward biased? Only when VD exceeds V gamma, right? In size. Okay? Correct? So when VD is say more than 0.7 volts, even just around 0.7 volts, just a bit more, then VD is going to forward bias the diode, right? And then current will flow. So notice that that's exactly what this second approximation is telling you. Till VD reaches V gamma, and then no further change in voltage drop across the diode, because once the diode is cutting in, a forward biased diode has no drop across it for an ideal diode. So there is no drop across the ideal diode. The only drop from here to here would be exactly equal to V gamma. Note that from that point also, V gamma should be connected this way because V gamma is a drop, right? From here to here, the drop should be V gamma, and that's exactly what this says. And then, of course, comes the third approximation, which is really not vertical; it's slightly slanted. So what you can do is replace it by this and a small resistance called RD, which is an RD is really nothing but slope of this tangent. Here again, the reverse, the V gamma, which has been connected in reverse, blocks current from flowing until V gamma is reached. Once V gamma is reached, the voltage drop between these two ends simply becomes V gamma plus whatever up there is across RD. So V gamma plus I times RD. So that's why you get a slanted straight line. Does that answer the question?
Yes, sir.
Okay. Any further questions?
Sir,
Okay, let me just do. Yeah. Regarding
the peak inverse voltage.
Sorry, I couldn't hear you.
Why-
Regarding what?
Peak
Regarding-
inverse voltage.
Sorry.
Sir,
Peak inverse voltage. Okay. Yeah.
sir, in case of full-wave rectifier, why the peak inverse voltage is equal to 2 dp? I did not understand that.
Okay. You mean when you say full wave rectifier, which one do you mean? The one with the which one is that? The one with the double tap transformer?
Center tap transformer.
With the tap transformer, a center tap transformer, right? By the way, this circuit, although is one of the circuits that's always something which you are taught even at say high school level, is actually not a circuit which is commonly used. I think I have already said why in the video, but can anybody remind me whether I have actually said why it's not used very often?
Well, it's expensive.
It's extremely expensive. Because a single tap transformer, properly center tap transformer requires very accurate machining. And while making a transformer itself is expensive because you need a metal core, you need a lot of wiring, and all that actually is pretty expensive, much more expensive than the diodes. But anyway, you do need a step down transformer to step down the voltage from whatever your mains give you to whatever voltage you want. But you cannot do anything about. But having said that, a center tapped transformer requires very high degree of skill in actual manufacturing, and that makes it a very costly piece of equipment. So this is often avoided. But anyway, if you were to use it, what would happen? Note that the voltage here is taken from the center, is above the center tap. So when this voltage is positive above the center tap, this is negative, equally negative, which is fine because then we said that when D1 conducts, D2 does not. Okay. So when D1 conducts, the current flows this way and flows through the resistance this way. So the current through the resistance flows from top to bottom. Of course, the value of the current changes because the voltage is changing, but it flows from top to bottom. When the input voltage cycle becomes negative, that is, this voltage becomes negative and this becomes positive, then current flows like this. Okay, but once again, the current through the resistance is always from top to bottom, which means the output will look like this. Now, the real question here, the question that was asked right now, is about the peak inverse voltage across a diode Let's say the diode D2. You can also work it out for the diode D1, but any one of them will do. So the question really is how much is the voltage drop across the diode? So whenever this is at plus V, this is at minus V, right? So when this end is at plus V, what is the voltage at this end? Assuming that the diode is ideal. The diode D1 is a forward bias diode. If you assume that it is an ideal diode, what is the voltage across the other end? Shomakanti Shah, you are saying minus V. Are you sure? When V is positive, D1 is forward bias, D2 is reverse bias. So what is the voltage at this point A? Sorry.
Plus V.
It is plus V. Why is it plus V? Because the forward bias diode behaves like a short. As simple as that. Remember, we are talking about ideal diodes, and if the diode is ideal, there is no voltage drop across it. So the forward bias diode has no drop. Whatever D1 is forward bias, not D2, right? So there is no voltage drop across D1. So if the voltage here is plus V, the voltage here is also plus V. Now tell me what is the voltage drop across D2? I thought this is a very trivial question. I've
Plus
told you
V
the
minus
voltages
of
are both. What?
2V, 2V.
Sorry.
Plus V
How much will
minus of minus.
Yeah, so it's 2V, right? That's a drop in reverse. This is a reverse biasing voltage. This end is higher than this end. So it's an inverse voltage. So the inverse voltage which you have given across a diode is twice V. At any given instant, when the input voltage is plus V from the center tap, the voltage across the other diode is twice V, right? Now, this V is an instantaneous value. It keeps on increasing or decreasing with time. But what is its maximum value? That's the peak inverse voltage, right? The peak value of the inverse voltage. So what is it? How much is the peak inverse voltage?
2V.
Twice, not 2V. 2V is the inverse voltage. Peak inverse voltage will be twice Vp. Whatever. So the maximum value this reaches is Vp. The important point is you're looking at this from the point of view of the output. This reaches a maximum value of Vp. And at that point of time, the output reaches a maximum value of Vp. Right? But when this reaches a maximum value of Vp, on this other side reaches a minimum value of minus Vp. The peak amount of reverse voltage. Remember, when you are talking about the maximum value of the difference between two objects, you have to take the largest value of one of them and the smallest value of the other, provided they occur together. Here, when one thing occurs, one thing becomes the maximum, the other thing becomes the minimum. That's great for us because that makes finding the difference, largest difference, very easy. You just take the largest value for this side's voltage and the smallest value for this side's voltage, which occur at the same time, and the difference is just twice Vp, two times the peak voltage. So here, what is very important is which peak voltage do I mean? Why is that an important issue? Because here, when I say Vp, I mean the voltage between the maximum voltage this point reaches with respect to the center tap, not the maximum voltage difference between the two ends of the solenoid, two ends of the output solenoid or the secondary coil. All voltages are measured with respect to this point. So when I say Vp, and that's important because, and that's also what you should do, because that voltage is exactly what you get at the output. This Vp, the maximum value which this voltage reaches with respect to the center tap, is also the peak value of your full wave rectified output. Is that okay?
Yes, sir. Sir, I have another question.
Yeah.
Regarding the repeal factor. Sir,
Sorry, I couldn't see.
in case of
Yeah. You said ripple
Sir,
factor, right?
in case of half wave rectifier, we find the ripple factor is 1.21. So, what is the significance of this digit?
Sorry, I couldn't hear you again. You said 1.21 then?
Sir, what is the significance of this digit? Means ripple factor 1.21. What does it mean?
It simply means that the RMS value of the ripple, the AC ripple, is actually 1.21 times the average value. That's it. That's what it means. Look, the basic idea is that the output, what is an ideal DC source? An ideal DC source should have a current or voltage which varies with time according to what law? Is this one ideal DC source? What kind of voltage would you want? As a function of time? But when you're talking of voltage sources, there are two different kinds of things that you would want. One is how does the voltage depend on time? The other is how does the voltage depend on the load current? And if you wanted an ideal DC source, what kind of voltage time dependence would you want?
It's a straight line parallel to t-axis.
The t-axis, right? It should be something like this. Although, yeah, completely flat, no variation whatsoever. While this is, by the way, this is DC. This is also DC. Current always flowing in one direction. Always positive voltage, but changing rapidly with time. Even this is DC nominally, both are DC. This one is also DC, this one is also DC. But the better DC, of course, is this one. Okay. The ripple factor actually tells you how close you are to an ideal scenario. In a real voltage source, you never really get a flat voltage curve unless you're using very, very high-end batteries. Okay. A real voltage source, especially one which you create by rectifying an AC, is always something which has some kind of waviness. Maybe an extreme amount of waviness like this, or a smaller amount of waviness as, say, in a half-wave rectifier circuit, or a full-wave rectifier circuit, or a circuit with a filter. Okay. But here, for example, you get a DC value which is quite small, and a rather huge fluctuation around that. The fluctuation is once you take the DC value away from the current, what you get is the AC value of the current. And the RMS value of that thing tells you how big the AC is. So a large ripple factor essentially means that you have a lot of AC mixed up with your DC. Despite the fact that the current is always flowing in one direction, it has a lot of fluctuation, a lot of going up and coming down. So if you look at the average value, deviation from that is a rather large amount of AC. And a ripple factor as high as 1.21 would tell you that there's a huge amount of AC here, but so huge an amount of AC that it would not really be a very nice rectifier. It would be very far away from your ideal behavior that you want. Okay, clear? Now a smaller ripple factor would mean that at least the fluctuation with time is smaller. So a full wave rectified output has a smaller ripple factor than this. Once you put in a filter, it has a much, much smaller ripple factor. So in that sense, you're getting closer to the ideal voltage source, ideal DC source. Okay. So basically, the ripple factor measures how much AC do you have mixed in with your DC. DC is what you want. The AC is unwanted. So a large value would mean bad circuit, at least not so good a circuit. Small value would mean a better circuit. Does that answer your question?
Sir, for ideal DC source, ripple factor will be 1, right?
No, for an ideal DC source, ripple factor would be 0.
Okay.
Because there will be no AC. I think you're making a mistake. I think you're confusing the RMS value for the whole source. I think what you're saying is IRMS by RDC. If you do that, right, then you will get a larger. Okay, I must correct myself a bit here. There are two different ways of defining the ripple factor. One which takes the entire RMS current, divides that by IDC. If you use that, then you will get 1 for the ideal source. Then any value which is larger than 1, or how much larger it is from 1, shows you how much ripple you have. But usually you don't do that. Usually you take the ripple, take the AC part. AC part means actually you take the actual I of t, subtract IDC from that. This is your AC value, right? And you take the ripple factor, take the RMS value of IAC and divide that by IDC. And that gives you the ripple factor. With this definition, the ripple factor for an ideal source is 0. Do you get my point? What is the ripple factor for a full wave rectifier? Do you remember that?
It's 0.4.
So if it's less than 1, then of course it has to be this definition. And this is the definition which makes sense. You don't really divide RMS value for the full current by the DC current. You divide the RMS part of the AC, the additional part over the DC, and then divide that by IDC. You should realize that the RMS value for the full current cannot be less than IDC. Or can be less than IDC. I'm wrong. Can it be less? Yeah, it can be less depending on the circuit. But anyway, that actually doesn't make much sense. This one, when you take the RMS value for the AC part, that makes more sense as a ripple because that tells you how big the ripple really is. Okay, there was a question in the chat. What does complex impedance mean? Let's say instead of taking complex part for solving AC circuits, we take only real cos or sine part as it is. Then in that case, what will be the impedance? Well, the real problem with this, Akhil, is this. When you send a current through, say, an inductance, the voltage is not proportional to the current any longer. The voltage is proportional to the derivative of the current. Okay? So we started with a sine, say cosine omega t as a, let's say we started with I0 cosine omega t as the current. Let's say this is your current. So what will be the voltage across an inductance? It's L di dt, as simple as that. And that's minus omega I0 times L times sine omega t. Notice that what has happened is you have got an omega I0 L with a minus sign in front. But what is more important is that you have actually changed the cosine to a sine. So in terms of the actual voltage and the actual current, the real values, this is not okay. So just like in the case of a resistance, on the other hand, VR would simply be R I0 cos omega t. So even with the sinusoidal input source, when I say sinusoidal, I mean a real sinusoidal source with cosine omega t as a time-dependent behavior. If you divide the voltage across a resistance by a current, by the current through it, you would get a time-independent R. When you do VL by I, you cannot do that. That is, you can do that, but it will not give you a time-independent quantity. It will give you something which fluctuates wildly with time. Right? It's actually a tangent of omega t. So it shoots off all the way from plus infinity to minus infinity. Of course, what you really are interested in is this. The amplitude of this is I0. The amplitude of this is omega I0L. So the amplitude of the voltage divided by the amplitude of the current, or the RMS value of the voltage divided by the RMS value of the current, that actually is just omega L, which by the way is the magnitude of j omega L, the complex impedance that we use. But if you just look at omega, you might say, then why bother with a j? We will just use real currents, real voltages, and say that the impedance is omega L, where it gives you the ratio between the RMS values or the peak values, whatever that is. Well, you could do that, but then you would lose another very important piece of information, which is when the current is cosine omega t, the voltage is minus sine omega t. That means it has actually an extra pi by 2 phase. Okay, so an additional phase shift. The voltage across the inductance actually leads the current through it, reaches to its peak earlier, and so on. Because this is nothing but omega L I0 times cosine omega t plus pi by 2. There's an additional pi by 2 phase shift. So you could of course say this. You could say when the voltage goes through an inductance, when a current goes through the inductance, the amplitude of the voltage is omega L times the amplitude of the current. And there's an extra plus pi by 2 phase shift. But notice that j omega L, the complex impedance, does exactly that. It has an magnitude of omega L, and it has a phase of pi by 2. Right? So both information about how does the amplitude change and how does the phase change, both parts are there in the complex impedance. And why does it work that way? Because when you talk of complex numbers, this is just the magic of complex numbers, or magic of the exponential function. It behaves very nicely under differentiation. Cosine and sine also behave nicely under differentiation. Right? Cosine and sine also behave rather nicely under differentiation, but not as nicely. Okay? Under differentiation, cosine and sine change. Cos changes to minus sine, sine changes to plus cos. Exponential stays just the same, so it's much easier to do the calculation in terms of exponentials. Is that okay? Does that answer the question, Akhil? So if you are using real voltages and real currents, you would really not talk of impedance so much. You could actually talk of reactance, omega L, which is a magnitude that gives the voltage ratio of voltage to current. But it's less useful than the complex impedance. Complex impedance has complete information of what's happening, both the amplitude and the phase. Okay, just before I let you all go, I will want to show you one thing. I've already given you a program for this Fourier series decomposition problem using parallel resonance circuit. I just wanted to show you a slightly fancier version of that program. Oops, I forgot that my keyboard is set to Bengali. Fourier_resonance.py is actually the program that I gave you. And this is just this program with a few additional lines, which all that it does is that it allows you to produce a slider with which you can change the frequency. Matplotlib allows you to do that. Rather simple, but notice what happens when I change the frequency using the slider. So this is the first peak that you get. So if in a real experiment you change the frequency, you would essentially see this. Then the current falls off as you move away from as a square wave. The blue line is a square wave input signal. And then you get almost zero for a long time. And then when you get to 600, why 600? Because that's 1/3 of the resonant frequency of your circuit. You had another peak. And in this peak, if you count, this is from here to here, that's one complete cycle of the square wave. That is always at 1800 hertz. Sorry, that's at 600, sorry, 600 hertz, 600 hertz now. But notice that the output that you are getting, in that, there are 3 complete cycles. Of course, this is not exactly 3 complete cycles, but that's because I've not got to exactly 600 hertz, where the real peak exactly is. But now you see, you get 1 complete cycle, another complete cycle, another complete cycle. 3 complete cycles of the output wave in 1 cycle of the square wave. Okay. Why is that? Because the input is at 600 hertz, that's this complete square wave, which has a 3rd harmonic, which is 1800 hertz, which is the one which is resonant. So you get something like this. If you go, now this is for a Q value of around 50. You can also use the slider to change the Q value. Now you see that when the Q value is rather small, what's happening is that the nearby frequencies, the other harmonics, are not being completely suppressed. So while you do get a resonance at 600 hertz because the 3rd harmonic, which is at 1800 hertz, is at resonance, the other harmonics are not so far away because of the small Q value, and so you get rather wavy kind of sine wave. This is something people see all the time in an experiment, and very often it puzzles them. Why do you see a wavy sine wave? The answer is the other harmonics are showing up. I will also upload this particular program to the website to VLearn. And you can, if you want, you can definitely take a look at the code. The code just has some additional lines which allow you to calculate, or which allows you to draw the slider, nothing else. The actual code is the one which you have already seen. I'll put this up on VLearn so you can play around with it if you have Python installed. Okay. So bye for now, and best of luck for the exam on Monday, which can be at 9 AM, can be at 9:30, can be at 10, 10:30, whatever. I'm not saying when. Okay. Yeah, okay. Go ahead.
Sir, I had a few more doubts. First thing is,
Okay.
why are we so much obsessed with 3 decibel? Why not some other?
With what? Sorry, with glass? With,
like we
why
talk
we so
about 3
obsessed with
decibel.
what?
3 decibel.
Sorry, I was speaking when you were saying that. With what? 3 decibel?
Yes, sir.
Is that what you said?
Like, why not 4 decibel or something like that?
Good. Why with 3 decibel? Because 3 decibel is really 0.3 bells, right? Deci means 0.1.
Yes, sir.
Okay. Now, what's so special about 0.3 bells? This is logarithmic. 0.3 is actually the log of 2. Okay. So when you say 3 decibel, you really mean half. That's what you really mean.
Okay.
Something which drops by 0.3 in the logarithmic scale actually drops by a factor of 2. No other reason. You could talk about 4 decibels or 6 decibels or whatever. But 3 is just a convenient point. 3 decibels sounds like another complicated number to talk about, but it's really because 0.3 is log of 2. And that's a logarithmic scale. 3 decibel drop means that the peak value has come down by a factor of 2. And then half, that's it. No other reason. Okay.
Yes, sir.
And
Another question. In 2-port system, we talk about fluctuations and ignore the part which average is 0.
True.
Like we talk about the fluctuations. We take only
Sorry,
like,
I couldn't
fluctuation of
hear
delta
you.
V.
You are breaking up a bit, so I couldn't understand exactly what you're asking. You could say that a bit slowly.
Am I audible now? Am I audible now?
You're audible, but speak slowly because you're breaking off from time to time.
Okay, sir. In two-port system, we talk about fluctuations and not the absolute value.
Sorry, couldn't hear you.
So I'll write that.
Okay, I think you're actually moving around a bit so that your mic is swinging or something. I heard two-port systems, but then fluctuations also, but I didn't get your question.
So I'm writing it in the chat box.
Okay. Fluctuations are not the absolute value. When you say absolute value, you don't really mean the absolute value. You mean the instantaneous value, right? You mean well, you actually do want to talk about the fluctuations very often simply because once again, if you're dealing with a nonlinear circuit, the response could be very, very complicated. But when you're talking about fluctuations from some standard value, then the corresponding response would be simpler. All you are really saying is this. If you have a complicated curve and you only talk about small variations from that complicated point, so basically you are looking at linear behavior. The two-port network can work for certain voltage sources only when there is some fluctuations, not really. It's just that when there is no fluctuation, it's very uninteresting. The fluctuation is really not a bad thing. The fluctuation typically is the signal. Typically, two-port networks are used to describe amplifiers. You have an input signal, you have an output signal. The fluctuations are really just those signals. So those are the ones which you are most important in. Okay, so Ritu, you had a hand or something. You want to say something?
Yes, sir.
Yeah.
Yes, sir. I had a small doubt about the Laplace transformation. It changes from T domain to S domain. So, what exactly is the S domain? It has any?
What is that? Sorry, I couldn't get you. What exactly did you say?
What is S domain? Does it have any significance, physical significance?
What do you mean by physical significance?
I mean, here.
By the way, no. T, of course, very often we use T for time, and that in that sense it has a physical significance. But this is a mathematical transform. T could be anything. Doesn't really matter. Okay. T could be any variable with no physical significance whatsoever. Even then, this would make sense. So S has no physical significance in the sense that can you identify it with a physical variable? But does energy have physical significance? You might say yes, right? But energy actually has only physical significance because it allows you to do some calculations, physical calculations or some physical results much more simply. Other than that, these are all derived concepts, no real direct significance. For example, you never measure energy, you only measure changes, right? That doesn't make it any less physical. It's useful. S is useful. Okay. And especially when you study advanced circuit theory, you will see that people hardly ever talk about T. They talk about S all the time. Okay. Say, for example, all these, in fact, they don't even talk about J omegas. Instead of J omegas, they use S. And all the calculations, all results are presented in terms of that. It's just that it's easier to work in terms of S. And then once you have worked it out in terms of S, you can actually easily go back to figure out what happens in the time domain. Okay. So is this physically significant? No, in the sense of being directly measurable, it's not physically significant. Is it physically useful? It definitely is. And after a while, frankly, physical significance that question actually loses significance. For example, would you say the wave function in quantum mechanics, what is the physical significance of that? The answer is nothing whatsoever. But it is related to quantities which are physically significant. Okay? That doesn't mean the wave function is not something which you can ignore as a physical thing. It is a very important physical thing. It's just that it's not directly physically related. to observations, but observations can be figured out in terms of that. Well, S is a more abstract thing than that, but even then, all I would say is S is important in physics because of the fact that it allows you to do calculations in a very easy fashion. So in that sense, it would be the same thing as asking what is the physical significance of a complex impedance. Things are really not complex, but they make life a lot easier. I hope that answers the question somewhat. Does it?
Yes, sir.
Well, you don't really seem very convinced, but anyway, think about it. Okay, anyway, bye for today. We will, I will meet you again on Monday, and best of luck for the exam.
Sir, I have another question.
Okay, quickly. Because,
I have put it in the chat.
you put it in the chat?
Yes, sir.
Well, why do we say two are independent, two are dependent? Because that's the most common situation. You could, if you really had 1 volt current which controls both sides, then the two sides would really not be independent input and output voltages. Okay. So just think about it. This is not the only possibility, but this is the most common possibility, especially in the amplifier scenario. And maybe when you see this, like when we use this for amplifiers, especially for transistor circuits soon, you will see exactly why this is being said. Right now, let's leave it at that. This is the most commonly seen situation. Okay, and now I must sign off because somebody else's class is being impinged upon, I guess.